Now from here, let me put it here. From these two relationships, okay, we're going to have V over change in V is equal to R over change in, V times change in T. Okay, let this V come here. So to be V into bracket V change in T equal to R change in V. This is going to give us V squared change in T is equal to R change in V. Let's rearrange. We get V squared over, let R come here, and then the change, so change in V over change in T. What do you notice about this equation? This is equal to acceleration, because acceleration is defined by change in V over change in T. So see that from here, the linear acceleration part, the linear acceleration can be related to the velocity, the constant velocity given R. Okay, linear acceleration here, which is changing this, can be related to, if it is a circular motion, we are considering R. That linear acceleration, if you want to connect it to a circular motion, then that constant R and that constant V and R will give an expression for A. So this is what I mean. From this, it's now clear that you can define and you can derive acceleration due to gravity from here. So that you can say that A is equal to change in V over change in T, this linear acceleration. So this linear acceleration, A, and this is equal to V squared over R. So if we are, this is an expression for all kinds of acceleration, and this is an expression for linear acceleration when we are looking at it in a circle. Because we have, so in a circle where the body is moving at a constant velocity, R becomes the next factor that defines acceleration, linear acceleration for that circular part. Good. Right, because if we leave it to just V alone, it will be 0, because V final minus V initial is 0. So R will account for, and we already said there's an acceleration, so R must account for, and then we can get the linear equivalent form of acceleration. Right, so this is an expression that we use. Now, so first, once we have this, let's look at other expressions. We're going to look at let's define in radians. We have already decided that for radians is when we are trying to get the angle in a linear magnitude form. We said if you have this circle, this is a radius, and then you move a distance s. Okay, this angle can be in degrees. Can be in degrees. It can also be made to be in radians. Okay, now let's assume this is radians. This theta in radians is defined as the distance that you have moved divided by R, and that will give you equality. So it's not distance is R is distance. This is also distance. So you are going to get it in linear fashion. So that angle has been converted to linear fashion. Okay. So by definition, theta is equal to, and by radians, theta is equal to S over R. S over R. Now let's look for, let's move on to what we call the angular magnitudes. Okay, so we have what we call angular velocity, then we have angular acceleration. Okay, so let's see if we can get some kind of equations that will relate linear measurements and then angular changes. So we are looking at the relationship between angular changes and linear measurements. Okay. Right. Let me clean up. I think this picture stay in your mind. You should have this picture. Immediately we talk about circular motion, let's have this picture and then this picture in mind, and then you are good to go. Right. So let me just clean that. Alright, so we have said in terms of radians, this is equal to that. We want to look at angular and linear measurements, how we can relate them. Now, we have what we call angular velocity. Angular velocity, and it's defined as change in angle over change in t. Then we have what we call angular acceleration. That is change in what? Acceleration is change in velocity. So this one is angle. So change in angular velocity over change in time. This is the same as final initial over change in time. If the time started from 0, then becomes this that over t. Of course, this is also the same as final t. Right. So these are the expressions. Now let's see if we can connect the angular measurements and then the linear measurements. Right. Okay, so from here, theta is equal to sine distance over r. Okay, let's look at this expression. Changing t over changing theta over changing t. So let's see. If we want to, we can have an expression like this so that it will convert this equation to angular velocity. So if we divide here by, if we make it like this, let's say, or let me put it this way. If we divide here by t, we have to divide here, or divide here also by t. And then this will become what? Angular velocity, because it's changing angle, equal to s over t times 1 over r. What do you get? S over t, distance over time is velocity. So this comes out as what? Velocity times 1 over r is equal to angular velocity. So this is going to give us an expression that relates linear velocity and angular velocity. So that we can see that from here, this is r. We can see that v is equal to r omega. This will come and multiply, so that r is what r omega. Right. So this is one way of deriving the formula for it. Okay. Right. So where we assume change is that t started from 0, so t is as it's t, and then this is representing the range t. Alright. We can also say that somebody could have also done this. T, after he's done that one, you can just find the t, and then with respect to different, that is multiplying here by the t. Okay, then this will be what equal to s over r, but we know r is constant, so that it becomes what? It becomes 1 over r s t theta t. This becomes angular velocity, and this becomes what? 1 over r and velocity. That's it. It's the same thing, and then we get in the answer. Right. So let's look at it. Let's look at the angular, the acceleration part. Now this is it. Now angular acceleration has been given as angular acceleration. There is it. Okay, angular acceleration is t. Okay. Right. So let's see if we can get an expression that will give us that will help us to relate angular acceleration to maybe linear acceleration. So let's see. So first we have angular velocity here, and then we have linear velocity here. If we differentiate this one with respect to t, let's say the v, the t, and then do the same thing for this. So we are multiplying by this expression. So we are differentiating this with respect to t, differentiating this side also with respect to t. Right, let's see what happens. Given the t, it gives us acceleration, linear acceleration. Okay. This is r is constant, is the radius, is constant, so it comes out and then you're going to d t. So what do we have there? Now, from this expression, this angular acceleration is equal to this is the same as the differentiation of differentiation of the velocity, angular velocity over the t is the same thing. This is the same expression. Okay, if I look at it, this is what you have here. It's the same as this one. So it means this expression can be rewritten as r times angular acceleration, so that this will mean a is equal to r angular acceleration. This is another equation of this. So this was the first equation. This is the second equation. What's the, look at it carefully. What do you see? V is equal to r omega, and a is equal to r angular acceleration. So you see that if these are linear, the linear magnitudes, okay, of course linear vectors, or let's say linear quantities, okay. Now these are the angular portions or the angular expressions. So you see that velocity, linear velocity is related to angular velocity by the constant r. Linear acceleration is related to angular acceleration by the constant r. So this can even be an easy way to remember the formula. If you don't want to go through the steps of deriving, it's an easy way to remember the formula. So it relates linear to angular, so this is angular, as we sought to do earlier. So we wanted to have a relationship between angular and linear. So this is the expression. So having had this, then we are good to go. Right. So this will bring us to the section on circular motion, so that when you are giving questions, you can use these methods to derive get the answers. Now let's move and then look at the simple harmonic motion. Now let's look at the simple harmonic motion. Because this one we can always look at it from the pendulum. So this is the event, this is the mass, okay, and it's swinging. It goes to this point and comes. When it swings here, by the time it gets here, velocity goes to 0, okay, and then moves here, comes here. So here it's v, the velocity gets to a mass, and then comes to 0 again, but in the opposite direction. So it goes back doing that. Now, when it's moving, if we look at it from here, we can look at it from in the y-axis. So this is the x-axis, this is the y-axis, okay? You see that it will, if we are looking at it, if this is the height, or at this point it is here. When it is coming down, it's here. When it's coming down, it's here. When it's coming down, it gets here. Then it starts going in the opposite direction. So there's a distance along this one which goes and then comes back. Okay? Right. Somebody can also look at it, the distance in the, what do you call it? The, maybe along the x. So from here is negative. When it comes here, that's some point, comes here, comes to the point, fixed point 0, goes in the opposite direction. Okay, fixed point 0, and then returns. Okay? So whichever direction you're looking at it, you can describe it as simple harmonic. So simple harmonic motion, first of all, there's always what? There's always the acceleration and velocity, they are directed towards a fixed point. Okay? It is not ever increasing, they are always directed towards a fixed point. So that will make that will mean your acceleration will be negative. Okay? You negate, if it's not ever increasing, you make it negative. Right, so that is one point we can look at. Now we can convert this the change in distance along the y-axis. We can look at it this way. Okay. Maybe it starts from here. So it can describe a circular path just like I said. If you have let's say a car here and it's moving this way, when it gets here, it has a certain distance y. When it gets here, certain distance y. Gets here, y motion. Then it starts coming down, goes in the opposite direction. Okay, and then it comes here. So you see that it is making the two. It started from here, it went there, came through this, came here, and then comes back by the time. So that will be more or less a circular motion. So that's the to and the to and the fro kind of motion describes a circle. Okay, describes a circle. Right. So the same thing like this. If this is coming, it's decreasing, then it starts decreasing, but this one is going in the opposite direction. It's going in the opposite direction. Okay, gets there and then comes back. Before it comes, so from here and then coming back, this is one complete move, and that is similar to a circle. So we can draw this one like that. Let's assume it moves from here to this point with an angle theta. Okay, with an angle theta. It should have made the distance it would have made along the y with this y. Okay, this is the angle. And then of course this is our radius. This is the distance. It will be the same throughout so far as so this motion we said is simple harmonic motion. It's to and fro motion. To fro motion. Okay, so the same thing. Go that way, comes back. So if you go and then come back to where you were, that is a to and fro motion, and that is simple harmonic motion. There's always the acceleration, the velocity and acceleration are always directed towards a fixed point. This fixed point, a fixed point, right? So that is the simple harmonic motion as far as I mean the point that I can talk about. So let's see, we can get a relationship. We have a theta here, we have the distance instantaneous. So these are the instantaneous distances that this angle. So for this angle, it has its instantaneous y at this, and it has its the distance here as r. There's a relationship between r, this and that. What relationship will it be? If this is our theta, this side is opposite, and this is hypotenuse. So opposite and hypotenuse. What relationship can you use? It's so can use sine. So it means that sine theta is equal to our y over our r, which is the same as what? R sine theta is equal to y. So that y is equal to what? R sine theta. Remember, y is the distance along the y direction, and this is r, which is a constant, becomes a radius. Now this expression is very important. We're going to depend on this to derive the other kind of equations. So let's see how that will be done. So we said for this circle, what you have that the body is here, moves to here, its distance along y will be this, which is the same as y here, and this is theta. We are saying that y is equal to r sine theta, because we said this expression is the same as sine theta is equal to y over r. So from that is what we are getting this. From that we are getting that. Now this is linear, this is a distance, this is distance. Of course, this is giving us an angle which is going to be a measure in terms of magnitude distance. Alright. Now, if you want to find velocity, let's assume you want to find velocity. You know, velocity is equal to what? Change in distance over change in time, which is the same as ds dt. Now, our s distance here is y. Okay, so we can say dy dt. This is where I want us to look at. So that we come back to this equation. If we differentiate this equation, if we find dy then we can differentiate this equation, right? But before we go on, this is in radians. Remember, we have already said this is equal to S over R. Okay. Now we know that let's find an expression for this. Omega is equal to this over changing theta over t. So that changing theta is equal to what omega t. Right? Good. So in terms of theta here, we can put this can also be written as R. I'm written as what R sine theta, which can be written as this. Okay. Now let's see how the differentiation will go. Right, so let's look at it from that. Now, so let's say to be able to differentiate this equation with respect to t, we must get t here in the equation so that we can differentiate with respect to t. So that we can say that from here, from here, dy dt is equal to, because we have t, we can't use this one because we should have t in that expression, is equal to we have already found out why this is split. Theta is equal to that. Okay, and this is going to be dy dt is equal to r is constant, so r comes out sine omega t over dt. Okay. Now, if we differentiate sine, it becomes what? Cos, positive cos. So r, and then the constant will come out. Okay, this constant will come out. So this cos omega t. And dy dt is the same as the velocity. So this is the velocity. So this is the first equation for simple harmonic motion. That is it. Now, if you want to find A, you know A is equal to what? dv dt. Okay? dv dt. Now, so it means we have to differentiate this one. Now so dv dt means we are supposed to differentiate this one. v dt will be the same as d bracket r omega cos ut over dt. dv dt is the same as a, already we have said. This is constant, so constant comes out. If you differentiate these two constants, so the constant coming out, okay? If you differentiate this one, if you differentiate cos omega t, if you differentiate this one, if you differentiate cos, what do you get? You get what? Negative what? Sine this. Of course, the constant will come out again. So you have to remember this. Let me write it well. Negative sine negative. Here's the answer we are getting. We can rewrite this one as a. Of course, it's negative as a is equal to negative omega squared. This time, this is omega squared r sine omega t. This is the equation for acceleration. So see that acceleration becomes negative. It's negative because the acceleration will not be ever increasing. It will always be pointed towards the direction. It's always pointed towards a fixed point. Okay, that's for simple harmonic motion. So there's it. Now let's see. You see that if you say this is going round at the point that it is maximum here, if it is maximum here, at that point the angle is what? What angle will it be? It will be 90. Sine 90 is the same as sine. The proportion of it is 90. If this one is, if this is 90 degrees is 90 in degrees, of course, equivalent in radians. Okay, then sine theta, sine 90 is what? 1. Okay, sine 90 is 1, so that you have A is equal to, if this whole thing is 1, then it will be A is equal to what? This. So at the maximum point, okay, this is the acceleration. So this will be the acceleration. Right. So you can use differentiation to make your work very simple. Then that gives you the formula for this, the simple harmonic motion. So that is, we are good to go with this equation. Right. The last part I'm adding, let's add some last part. Let's find the relation between T, omega. We know that frequency is equal to number over time, number of cycles over time. Okay, what we are considering for this angle, if what we are considering is a circle, then we have the number of times there over this. Okay, for one complete revolution, or one complete, let's say for the time taken for the number of, let's say, in terms of making one to and fro, or one revolution, or one distance around the circle, that will be one. So this will become one. This time, the time that it takes to make one frequency is T. So that you realize that F is equal to 1 T, or inversely proportional to T. For one revolution, the time taken, the T becomes T. The time taken becomes capital T, which is period, and then this is the frequency. Good. Now, we know that theta is equal to distance over r, and then we found out that omega is equal to this over T. Okay. Now this will mean, let's put this expression for this one. It will mean S over T, which is what? S over RT. Okay. Now let's see. For one revolution, for one ten, if it is 110, this distance becomes what? 2 pi r. And time is r. Time becomes capital T. Right. So in that case, this r will cancel this, and then we have what? 2 pi over T. We said omega is equal to that, so omega is equal to this. This is expression in terms. So that we can say that omega is equal to 2 pi over T. This is expression that we'll be using in most of our equations. In other words, T is equal to 2 pi over omega. Now let's see how we can find the period for this kind of equation. So let's assume for this our pendulum, it moves, that's mg, this distance is here, okay, this is it, okay. Let's see, it means this angle, very small angle, okay, so this is a pendulum, it moves with a very small, this is very small, okay, and very small, okay, and this one is what it has. And it moves, we have a tangent there. This is another angle. Right. Now, if we assume this is the force of gravity acting on it, this is mass m. Okay, when it is here, this will have a certain angle. This angle is supposed to be 90 degrees. You know this angle is supposed to be 90 degrees. Now look at this. This angle and this angle are corresponding angles. Okay, so this is our magnet. This is the hypotenuse. Okay, if we want to find this, it means this angle is going to be 90 minus theta. Okay, right. Now this and that will be added. That will be this angle adjacent and then hypotenuse. Okay, this will also, if you want to find this one, but we are interested in this. Okay, so we are interested in when it moves up. We are interested in that, so that we can see force is equal to mass times acceleration. Okay, this case is m times g. But what will be the, when it is here, when it gets to the maximum, this, the force here will be this. It will be related to this, the component of this here will be related by cos from here. It will be what? The force, which is mg, will be equal to, or let's say, this will be equal to cos 90 minus theta is equal to hypotenuse, which is h, which is our mg, okay, over our adjacent. It's opposite adjacent is car from the word car. Adjacent, so adjacent, let's say this is adjacent over our hypotenuse, which is h mg. So this will be a force in the force here, this force, Fa, let's call it Fa. Okay, so that Fa is equal to mg, this will come out by cos 90 minus theta. Okay, cos 90 minus theta is the same as what? Sin theta, because cos and sine, when you put them together, I get 90. So 90 minus theta, that means sine of this is the same thing. So this will be the Fa. So when it gets up, the force that will be bringing it back to the fixed point is this. And so force is equal to m times acceleration. Okay? Good. Now because this is to and fro kind of equation, our acceleration becomes what? Negative. So we have mg sin theta is equal to negative ma. Right? We have an expression for acceleration and then omega, which is what? Let's look at it. Now, right, so from here, right, we can, if we are given general equation, let's say this is, okay, let's say this is where we are now. Now, if we are assuming it's simple harmonic motion, of course, acceleration becomes negative. We can make it out. But we remember that we said at maximum acceleration is equal to omega squared from the previous one, where we said A was equal to omega squared sine this. And then we said if this one is 90 degrees, it will come back to this, then it was negative. Okay? And so it was negative. Okay, so we can put this in place of A here. So this becomes